Revisit an historic watershed in the study of the origins of life. Discover a program to expose high school students to careers in health and medicine. Explore how computer games teach computer science. Meet the winner of the Fields Medal. And plans for the world's first outdoor shake table. All on this edition of OnBeyond. "50 years ago, in the spring of 1953, the world experienced a breakthrough that would blaze a new pathway for science. In May, a young graduate student, Stanley Miller, published the results of a now famous experiment he conducted at the University of Chicago as a student of Harold Urey. What did he do that created the interest that continues to thrive today? As one of Stanley Miller's first graduate students, Jeffrey Beta, now professor of chemistry at UCSD's Scripps Institution of Oceanography, has an intimate perspective of this watershed in science and scientific thought. For nearly 40 years, he has pursued investigations into the origins of life, a field of science that the Miller-Urey experiment brought to the forefront a half-century ago. In a recent article in the journal Science, Jeffrey and his colleague Antonio Lascano commemorated this event, the context in which it happened, and the context that it created.
Well, there had been a lot of work in the 19th century on this synthesis of simple organic compounds, and this was driven primarily by the desire to understand how you could make compounds that were known to be part of living organisms or whatever in the laboratory. And as far as is known, none of these people really had an interest in the question of the origin of life or whether this chemistry might in fact be associated with natural processes. And that really changed in the 1920s when Alexander Oparin, a Russian, and Haldane, an Englishman, published simultaneously almost a thought that organic compounds would have been made directly on the early Earth by natural processes. These could have accumulated in the ocean, making so-called prebiotic soup, and from this prebiotic soup somehow living entities appeared by just complicated chemistry. And that's sort of where the field stood in the early 50s.
Things changed in 1951 when Harold Urey presented a lecture about the chemical events associated with the origin of the solar system, where he suggested that the early atmosphere may have been a reducing atmosphere, containing methane, hydrogen, and ammonia.
Stanley Miller was in the audience for that lecture, and a year or so later, he approached Urey about trying to mimic the early Earth using this reducing mixture. After some hesitation, Urey finally agreed to do this and sponsor this experiment, and all the rest is kind of history. When Stanley and Harold started thinking about the experimental design, one of the things they wanted to do was make this representative of the Earth's ocean atmosphere system. And so what they decided to do was have a flask that contained water, and this would be a mini ocean if you want to think of it. And that was connected by a glass tube to another flask, a bigger flask, that would represent the atmosphere. And then there was another tube that took and connected the atmosphere flask back to the ocean. And if you think about how the ocean works, you get evaporation from the surface of the ocean, the water condenses in the atmosphere, falls on the continents as rain and precipitation, and that ends up washing back into the oceans. And so you have a cycle here. And so that experiment was designed to mimic that. So you took the water flask, you boiled it, that generated a water, steam atmosphere. You introduced these reducing gases like hydrogen, methane, ammonia, and then you spark the mixture to simulate lightning or coronal discharges. And then all of this stuff, as it formed in the atmosphere, was washed back into the ocean, where In fact, the chemistry really took place. All of the synthesis of amino acids in the Miller experiment takes place in the water flask. And so that's really telling us that the chemistry, if it took place on the Earth, would have taken place in the ocean. I think the remarkable thing about it, you look at the apparatus, it's a very simple design. It's designed to mimic the ocean atmosphere system on the Earth. And it took them maybe a month or two to have the glassblower make this piece of apparatus. And when Miller first set this up and ran it, he ran it for 2 days. And right away, he got a positive result. One of the things he noticed in the flask that was supposed to simulate the ocean was that he could detect the simplest amino acid, glycine. And when he showed these results to Urey, Urey was just incredulous. This was a fantastic result, just what he'd hoped for. And so he had Miller repeat the experiment, this time running the experiment for a week. When Stanley analyzed the mixture at that point, he found that it contained several different amino acids, and he was able to identify 4 of these. And this really was a beautiful demonstration of how you could make simple organic compounds from a very simple simulated early Earth environment.
To commemorate the 50th anniversary of these astounding results, Jeff, along with Jim Cleaves, who was Stanley's last graduate student here at UCSD, recreated the experiment under Stanley's supervision, attempting to replicate his original conditions as closely as possible.
There were 2 goals in recreating the experiment. One was to demonstrate the simplicity of the experiment, which is one of the reasons it had such remarkable impact. The other reason was to see if, using the more sophisticated analytical techniques that we have today, we could detect a wider range of products than Stanley was able to in 1953. The first step in recreating the experiment was to take the apparatus and put it under as great a vacuum as we can get. And we'll close it off and leave it overnight to make sure it's not leaking. Because there's a slight danger that if you introduce oxygen into the apparatus, as it's filled with methane, which is natural gas, you can have an explosion when you spark it. So we want to make sure that it's absolutely airtight. Once we've done that, we introduce about half a liter of water. It's double distilled water, so we know that the only compounds in there are going to be water and the gases. There are no contaminants or trace metals, anything like this. Once we have that, we put it under vacuum to release oxygen that's dissolved in the water. So once we make sure it's completely degassed water, we can start adding the gases sequentially. And what we do is we add measured volumes and pressures of hydrogen, methane, and ammonia until we have the complete system. And we close it off and cross our fingers when we start sparking it. What we use to generate the electricity is actually a Tesla coil, and it generates a high-frequency electric discharge that produces enough of an amperage to create radical reactions in the gas phase inside the spark discharge apparatus as the spark jumps between the 2 tungsten electrodes. One of the first things you see is a slight yellowish tint in the water as something is getting dissolved in there, organic compounds that are generated in the gas phase. And you also start to see little filaments of organic material coming off the electrodes that seem to be sticking and polymerizing in place. As time goes by, you suddenly see sputtering organic droplets appearing on the side walls of the flask and a gradual buildup of a darkening color in the solution. So I think what happens is in the gas phase, you have ammonia and methane recombining to form cyanide, hydrogen cyanide, and then you have water vapor and methane recombining to give formaldehyde. And these compounds get condensed back into the water flask where they react in the aqueous phase. And it was determined fairly early after the experiment was first run that the mechanism of the amino acid synthesis is a reaction of an aldehyde with ammonia and cyanide that's then hydrolyzed to give an amino acid. But most of the chemistry does occur in the water phase.
After the experiment was completed, Jim subjected the products to a modern analytical technique called high-pressure liquid chromatography, or HPLC.
Today, HPLC is pretty much the one of the workhorses of analytical chemistry, that it's used for drug testing, it's used for medical diagnosis, environmental monitoring, and routinely in laboratory chemical preparation. When Stanley originally did the experiment, he could detect probably milligram quantities of amino acids. So that's 10 to the minus 3 grams, right? We can now detect probably about 9 orders of magnitude greater. So 10 to the minus 12 milligrams of compound. This is a pretty good increase in sensitivity. One of the remarkable things we found is that there really is a very small product mixture that's very similar to the one that Stanley detected in 1953. And even though we can detect a lot of compounds at lower levels, those products that he detected are actually produced in such an excess that they stand out as the major products. So it's remarkable that his analysis was actually very accurate, especially given the techniques of the time.
From one of his first graduate students to his last, Stanley's experiment has influenced generations, and it will continue to do so into the future.
Well, if you look at the impact that experiments had over the last 50 years, one of the things that just is amazing is the variety of organic compounds that have been made, the types of environments that have been used to simulate the Earth and other planetary bodies, interstellar medium. It's really, really set the stage for a huge amount of work and trying to understand natural chemical reactions in the universe. We now know that there's organic molecules around in interstellar space. They're made by a variety of reactions. We know there's organic compounds on asteroids and meteorites. And all of this knowledge has contributed to helping us understand how this chemistry may have taken place on the early Earth. And it can all be traced back to the 1953 publication of the Miller-Urey experiment.
Well, I think the Miller-Urey synthesis really stands as one of the touchstones of modern prebiotic chemistry. That even though some of the premises of the experiment are questioned now, the correlation of this experiment with really natural samples that we found on meteorites really suggests that this has some meaning, that it is really a process that takes place somewhere. And when we try to put together a narrative of how life began, we actually really do have a good sample of compounds that we know were probably available for the original life. And we found them 50 years ago.
Professor Boss, can you give us the background on the CEPA program?
CEPA stands for Science Education Partnership Award, SEPA. It was initiated by the National Institutes of Health as a way to increase the number of underrepresented minority students who enter health-related careers. We have specifically formed a partnership between a medical school and, in our case, Helix High School in La Mesa and Morse High School in Southeast San Diego. Our partnership is at the 10th, 11th, and 12th grade levels of students. In the 10th grade, we have faculty from the School of Medicine going to the schools and providing lectures on an assortment of health-related topics. In the 11th grade, we have students pick one of the topic areas that they've had lectures on, and they are expected to go in depth and study about that, mostly through online learning. Then in the 12th grade, what we do is the students now take what they have learned and they disseminate that, they teach that to younger students in the 5th through 8th grade level. So we sort of have a built-in peer teaching model as part of this.
They've all chosen an individual topic that they wanted to research. The topics all have something to do with health. They're usually topics that are of interest to adolescents, and they have attempted to find out something about how to educate their peers or kids that are younger than them in some of these health topics that they are interested in.
My topic is tattoos and body piercings, and basically it's going off like the harmful effects, and it's basically like an overview of what people should think about before they get tattoos or piercings. It talks about hepatitis and tetanus and keloids and how to clean them and how to take care of them and all the other necessities before you get an actual tattoo or body piercing.
The project I'm working on right now is just basically, I go to Le Mans classes and I have a pre-survey, a pamphlet, and a post-survey, and it's basically just to figure out if expectant parents know about learning disabilities, if they feel that there's a need to learn about learning disabilities, if they think they might have one, etc. It's just to figure out what they need to have if they find out their children do have learning disabilities, because learning disabilities are very hard to identify, especially at a very young age. You usually don't figure out that a person has a learning disability until about 3rd or 4th grade, when they start learning how to develop sentences, express thoughts through writing and spelling, anything like that.
My project is basically, it deals with ocean health, and I started out kind of broadly. I didn't realize how broad I'd started out until I had to actually get down to doing the work, but what it's come down to is basically whether or not certain bacteria, such as coliform and enterococcus, I believe you pronounce it, whether or not it's risen in recent years in our local beaches. And so I basically used the survey that the San Diego Department of Environmental Health created about 3 years ago, and their results, and I took that, and I basically created teaching tools to teach middle schoolers about how to protect themselves, what the dangers are that are out there when they go to the beach, and how to make sure that they don't get sick themselves.
These kids, these 12th graders, have gone in and they've chosen various topics, and they've talked to 7th, 8th graders, 6th graders about those issues and been able to answer questions. That's normally called service learning. And it's kind of like the student health advocates that are coming to this level. These kids are going to a little bit lower level in the hopes that those kids will listen to them. And hopefully they'll listen to them better than they would listen to an adult. And on some of these topics, they will. And that's the whole idea. Can we get through to these kids in a different way so as to make a difference? And we think that if we use the power of students to educate other students, then it'll get through.
What types of health care issues are you bringing to the school? That first contact with the
faculty at the 10th grade level. We have 4 separate units, as we call them. The first one is biopsychology, in which various topics are addressed, as, for example, drugs, stress in the teenager's life. Actually, we even get into things like domestic violence, topics that the students can relate to, actually topics that the students asked us to discuss. The second unit is called cancer genetics, and we talk about various kinds of cancers, again, those that the students are interested in and those that we relate to their curriculum. For example, if the students are talking about environmental health exposures, particulates in the air, then we will have one of the faculty come and talk about lung cancer as an example. The third unit is infectious diseases, and there we talk about the diseases that the students are particularly interested in. For example, herpes would obviously be one that they are very concerned about, HIV as another, and we have an infectious disease specialist who talks to them about that. And the fourth unit is broadly termed adolescent health, in general, health issues that the students are concerned about that don't necessarily fall into one of the other categories. Just sort of basic kinds of health-related matters that they are interested in. We let them guide our talks and our discussions. Throughout all 3 grades, the students have field trips that they come to the UCSD Medical Center, as well as coming up here to the UCSD campus. The field trips to the medical center include visits to various parts of the hospital. as well as actually sometimes going on rounds with individual physicians at the medical center.
What we're looking at now is, that's the tumor right there. These fatty tumors are not real vascular, which means they don't have a real big blood supply. And as long as it's not bleeding badly, we'll just keep pulling it up in pieces.
The field trips here to the UCSD campus are coming to laboratories to see what basic science is about, how science is performed, as well as to medical student teaching laboratories where they actually get to see and handle various organs, brains, hearts, etc., from patients.
It seems that the CEPA program has a two-pronged mission. When you're in the high school, you're doing preventive health care seminars, and then there's also the promotion of possible health care careers for these students later.
We feel the two together are very closely related, and although you could certainly call them two-pronged, the idea is by getting the students interested in health-related issues, ones again that they ask for, then they will become more interested in a health-related career. So the two are sort of go hand in hand as we look at it.
I understand that you have very realistic ideas about how much you can promote a healthcare career to these students. You're not trying to make them all brain surgeons,
no,
necessarily. But what's sort of the philosophy behind the exposure to careers in the health field?
When we take them on the field trips to the medical center, we take them on tours of various parts of the hospital, including the cast room, where they see people working there, the technicians on putting cast on patients, and they do much, much more than that. We take them to the laboratories, where they see all of the support personnel that are required to take care of patients. We take them to the pharmacy, we take them to radiology, we take them all over the hospital, so they see that a hospital is much, much more than doctors and nurses. Clearly, we would be very pleased if some of these students chose careers as either physicians or nurses, but there is so much more that goes into making up a hospital, and so we will also feel that we have been successful if the students choose careers such as an orthopedic technician or a radiology technician, because in those fields there's also a disproportionately low number of underrepresented minorities. So any way we can sort of have people become interested in health-related careers, I think would be all to the advantage. It's too early to tell yet whether or not we've been successful, but based on questionnaires that we give to the students, it certainly seems like we have been. And one of the things, very simply, that we do before they enter the program, we ask the students to list as many health-related careers as they possibly can. And not surprisingly, doctors, nurses, dentists, etc. are on that list. But after that, the list really does kind of peter out. But after they've been on their tours, the list is much, much longer, and it shows that they are now well aware that there are a large number of health-related careers in which they could potentially enter and have a fulfilling career.
I kind of came in the very beginning as like, oh, I don't like science at all or anything like that, and I wasn't interested in being a doctor or medicine. And I came into this year and I did my own research, and I found out like there's a lot more fields out there than I had originally thought. I mean, I knew there were more out there than just doctors and nurses, but I've kind of become more interested in just science and stuff like that. I don't think I'll be a doctor, but I have gained more awareness about the whole issue.
One of the other field trips we went on was to the public health lab, and the speaker there was pretty interesting. She got me thinking about epidemiology, which is, I guess, more of a social aspect of it, of learning about infectious diseases and how they go through the population and stuff like that, and that sounded like a lot of fun, so I've been leaning towards that.
What else do the students do after the field trip?
After field trips, they're expected to write reports and to tell sort of what they liked about it and what they didn't like. And then that serves as another purpose, that it allows us to improve the program and find out which parts of the field trip are particularly successful and which ones we need to try to improve on. What we're also having them do this year is to create pamphlets in which we expect them to make some kind of little flyers, brochures actually, if you will, that can be distributed to lower grade students that will be catchy and will draw the attention of the younger students so that they will now hopefully be interested in reading about this health-related topic, whatever it might be. We actually have quite sophisticated equipment at the school that we were able to purchase with the funds from the CEPA grant, and therefore the students can actually do publication quality work.
And this program has been going on for a number of years now.
Yes, we are now in our fifth year, beginning of our fifth, early on in our fifth year.
Has there been any specific students that have been a surprisingly successful response to the program?
Yes, there have been actually quite a few actually that come to mind that have, when we started out, we were a little bit concerned about the student, thinking that they weren't interested at all, but they've turned out to be some of the more enthusiastic ones. Several of them now are in college, and we're going to track their careers and follow them and see exactly what they do choose in terms of their ultimate profession, vocation, whatever they do. So that is built into the part of the program to track them even after the CEPA award, the funding is over. We will continue to track the students as best as we can. Obviously, there'll be some attrition because some of the students won't respond to questionnaires or we will lose their addresses, but to our best possibility, we will certainly follow them as long as we can.
Helix High School is a charter school.
Correct.
Do you think something like the CEPA program would work well in normal public schools?
It can certainly be done in a non-charter school. As I said, we were doing it at Morse. And other of these 55 CEPA programs certainly do use non-charter schools. They are different programs, mind you, but nevertheless, I don't think this requires a charter school. There are some advantages of charter schools, however. They are more flexible, they can be more responsive to changes, but I think the same thing could be done with non-charter schools as well.
Since the CEPA program is about to expire, what would you hope to see in the future?
The way the funding works is it's a total of 6 years, and so we, as I say, are in the beginning of our fifth, so we have another year and a half or so of funding on the CEPA program. As I mentioned, we want to follow the students and hope that we can see some success here. And we are considering alternative ways to continue a similar program. It may have to scale it down somewhat, although a good part of the funding was spent on equipment, and that will still be there. But some of it certainly is personnel, operating cost as well. And there are other potential funding mechanisms to obtain. For example, if we really can prove over the next couple of years that we have been successful, then I think other both private as well as public agencies might be very interested in continuing to provide funds because if the program has been successful, then that certainly is usually the thing that will allow people to want to continue to support it.
That's great. I want to wish you the best of luck in the future. I know you have another year left, and I hope you can keep the effort going.
Okay, thank you.
They're video games you won't play at your local arcade, on your Xbox or PlayStation, or even online. First-person shooter games like Shrapnel and Robostrike, racing games like Los Cartos Locos, or classic strategy games such as Spellcraft or IO. That's because all 5 games were designed by computer science seniors at UCSD as their main requirement for one of the hottest courses on campus.
It was probably like my biggest time commitment on anything ever, I think. Spent, up till 2 in the morning every day, just working on the game. It's a lot of fun. Out of all my courses, this is one that taught me the most. I spent the most time on, was the most difficult, and also the most rewarding.
They're in their last quarter of their senior year in college. You know, what they really want to do is graduate and move on. But they're in here for full 10 weeks, working day and night, trying to get these games to work. And in the end, they all succeed.
Jeff Volker created the course, a popular professor in the Computer Science and Engineering Department at the Jacobs School of Engineering. He teaches fundamentals of programming. This class on operating systems, for instance, is a prerequisite for Volker's senior-level project course held just once a year. Only 30 students are accepted, but 2 or 3 times as many apply. The course is called Software System Design and Implementation, but it's known better on campus as the video game course.
They get to take everything that they've learned as an undergraduate student in our major and apply it to something that they're very excited about, which is building large-scale, multiplayer, network, real-time 3D games. They take all the knowledge they learned about algorithms and operating systems and graphics and networking, and in this course they take it and they apply it. And they don't just apply it to a project that we specify and they have to do, they apply it to something that they're very excited about and very passionate about.
The class splits into 5 teams. Programming in C++, they must write 5,000 to 10,000 lines of code for an original online game that must be playable by at least 4 players simultaneously. Team members report and meet weekly with Volker on their progress, but otherwise are left to their own devices.
We essentially give them a blank slate, and they have to fill everything in. And that goes from what you see on the screen, the type of game that you wind up playing, the goals of the game, what you see, how you interact, and how everything is implemented underneath the covers. Often projects in other classes are very well specified. You are going to implement this, and here is how you're going to do it. In this course, it's just the opposite. All I tell them to do is they have to write a game that is able to support 4 players, and they need to do it in 10 weeks. They're writing thousands and thousands of lines of code at a relatively rapid pace, and often things just go wrong, and it's really tough to track down why. They run into bugs that aren't well known, and certainly I don't know the answer to their problems. And one of the things that they have to do is they have to learn how to solve the problems themselves. First identify that it is a problem, figure out what the problem is, and then somehow through news groups, the web, emailing authors of code, go out and figure out how to solve this problem on their own. I can give them encouragement, I can give them leads, but I can't give them the answer.
Volker tries to balance out backgrounds and personal interests, breaking each 6-person project into teams.
Students who work together are able to look over each other's shoulder and catch mistakes that they make, catch bugs early on and fix them, and more than one person has an understanding of how that part of the game actually works.
Each member specializes in one of 3 areas: graphics, underlying software, or networking.
There's the graphics part that everybody sees, but behind the graphics part there's a simulation environment to simulate the game. Since it's multiplayer and networked, there's a networking component. The game itself is relatively complex. It's multi-threaded, so all the threading that they learn and concurrency and synchronization that they learn in their operating systems course, they're going to apply here just to be able to handle multiple players running at the same time. It's a very large software project, and software projects are complex. And managing that complexity takes a bit of both technical talent as well as creativity in managing that kind of software.
After graduation, most computer science students end up working on large, complex projects that require teamwork and organizational skills. Volker says the video game course is a dry run for the real world.
The skills that they learned in this course are applicable not only to going into a games company and working for games, but any sort of software engineering position that they might go into. One of the explicit goals of the course is to have students work on a project that is unlike any of the other projects they've worked on in any of their other classes. It's something that they will be doing all the time when they go off into industry or the next stage of their career, whether it is programming at a company or it's in graduate school working on research. These are students that I'd love to work with in graduate school, that companies would love to hire.
While the course gives students a good sense of what it takes to design a game from scratch, Volker insists that it's a lot more than fun and games.
For the most part, students see it as a fun project. A lot of students who go into computer science, they've grown up playing games, they like to play games. This is a hobby that they have had, that they'll continue to have. But only a few students out of the course are really interested in going into the games industry as a profession.
For those who want a career in game design, Volker gets top industry executives to come in and give students an insider's look at how it works. In 2002, executives from two San Diego-based companies, Sony Online Entertainment and Angel Studios, talked to the class. Sony Online Manager of Technology Matt Sievertson, who got his bachelor's degree in computer science from UCSD in 1999, researches new technology for the company best known for EverQuest, its massively multiplayer online game.
Well, when I spoke to the class, I mainly focused on how making a massively multiplayer game, which is what we focus on in this company, is different from a standard either multiplayer or single-player game. They were all very enthusiastic about it. And there was no shortage of questions. We actually ran out of time.
Sievertson is now working on the next generation of EverQuest, as well as an upcoming online game called Star Wars Galaxies. And after seeing Volker's students make their presentations last June, he hired two of them. Sievertson says he appreciates that they came in knowing the basics of how to create a video game and with a major project to show for it.
To me, the biggest thing is that that class is a lot of work. It takes a lot of time out of their day. And you know that they really like video games if they completed that course. And that's something that we want here. We want people who are enthusiastic about the gaming industry.
One of the new recruits to Sony Online is Andy Skirvin. He now designs games for third-generation cell phones, even while he works on a master's degree at UCSD.
It's the one class at UCSD that I took in computer science that actually approximated like a real-world environment. You have a team of 6 people, and everyone has their roles. It's a very self-motivated class. The professor doesn't, he doesn't make you do the work. It's the class that kind of makes you do the work.
As a senior, Skirvin worked with 5 other students on the racing game Los Cartos Locos.
This is a multiplayer kart racing game, and the idea is to go around the lap and win the race.
The students for the Los Cartos Locos game indulged very creatively. They have lots of billboards that have lots of funny signs and jokes, and they have lots of funny sound bites that happen that they play when you hit an oil slick or something like that.
Sumit Singh and Chris Rosner worked with Andy on the racing game.
I had never really worked on components like sound or graphics because you usually don't get to, especially in class projects. So that was something new which I was going to be doing.
This class has taught me a lot about what it involves to be on a big team project, how much actual work is involved, and what sort of skill set you need to succeed in making games.
Among other games produced by Volker's most recent class, Spellcraft and IO are strategy games, although IO is turn-based while Spellcraft has everyone moving at the same time. And there were 2 so-called first-person shooter games.
In Shrapnel, you're in a souped-up spacesuit inside of a rotating spacecraft orbiting around a planet, and you're in teams going around trying to hunt down the enemy and eliminate the enemy before they eliminate you.
Panayoti Haritatos and Tim Foley worked on Shrapnel.
I'm a game player. That's what I like to do in my free time, and the chance to make games, obviously. I think I have somewhat of a creative nature, so the chance to actually be involved in making a game is something I've always wanted to be able to do.
When you're enjoying what you're working on, it doesn't matter how much work it takes. You're going to do what you can to make it be the best end product you can come up with.
Robostrike is another classic sort of first-person shooter. It just so happens that they made the context of the game be the UCSD campus. So in the game, they have a very nice model of the library, for example. And you just go around, there are mutant robots that have gone out, and you have to take care of shooting down the mutant robots.
The course whet many students' appetites for more. Of the 5 students interviewed for this story, 1 is already working in the video game industry, and 3 others hope to follow suit now or after grad school.
Everybody tells you that game programming is the most demanding, worst-paying programming job you can find, and it really takes dedication. And so I kind of took this course to find out whether or not I had that kind of dedication.
Does he?
Definitely.
The students did great. They not only met my expectations, but they far exceeded them. It's just amazing to see what they're able to do in just 10 weeks. This is the reason why we have the curriculum that we have in the computer science department, is if you go through the curriculum, then by the end, you have the skills and the talent to be able to do a kind of course like this.
Honestly, you know, if I'm looking for a new hire right out of college, the first place I would go is to see who's coming out of that class and see what they've done there. Because that's, you know, they're going to know what needs to be done, and they're going to have a step ahead of everybody else.
Welcome. My name is Jeff Remmel. I'm the Associate Dean of Physical Sciences, and I'm a professor of mathematics. And we're here today to talk to Efim Zelmanov, who is a recent recruit at UCSD. And one of the reasons that we're so excited to have Efim here is that he is one of the few people who won the equivalent of the Nobel Prize in Mathematics, which is the Fields Medal. The Fields Medal is something that is offered every 4 years at the International Congress of Mathematicians. Every 4 years, either 2 to 4 people win the Fields Medal, and this is considered the highest honor in mathematics. It's one of the most difficult prizes to win, and moreover, you have to be under 40 to win it. He started out his career in Novosibirsk. He got his PhD in 1980 in Novosibirsk, which is in the middle of Siberia. It's a major research center at the time in mathematics and science in general. And we are particularly fortunate to be sitting here in an office which has had 3 other Fields medalists.
It has the highest density of Fields medalists per square meter.
That's right. Since 1960, there's only been 36 Fields medalists, and we've been fortunate enough to have 3 of those. One was S.T. Yao, one was Mike Friedman, and the third one is Efim Zelmanov, who we're talking to today. And in fact, they all had the same office. Unfortunately, 2 of them are now gone, but we're very happy to have Efim here at this time.
Well, I'm very proud to be in this office.
You were somebody who made, who obviously made a major impact at a very young age for mathematicians. And even your thesis made a major impact in the field of algebra. When did you first, as a youth, realize that you had real mathematical talent, and how did that get developed in your school system?
Well, maybe in the 5th grade, when I was 12, I decided that I want to be a mathematician. And the reason was that I had a very good school teacher. Well, she wasn't much of a mathematician, but she was so enthusiastic and such a nice teacher. I think that played a major role. It's very important to have a good teacher.
Yes. And then how did the system, how did you go to university? Was there competitions to go to the university?
Yes, there was a good system of school Olympiads. You know, all school children in the Soviet Union could participate in Olympiads, first on the district level, then on the region level, and so on. So that's what I did, and well, if you are relatively successful, that's an indication that maybe you can continue. I was also fortunate that there was a good university in Novosibirsk, maybe the 3rd in the country.
You mentioned that you first decided you wanted to be a mathematician in sort of 5th grade when you were about 12 years old. And what was it that excited you at the time? What was it that attracted you to the subject?
Well, it's very difficult to explain the beauty, and I don't have to explain it to you, of course, but the beauty of a mathematical proof. You just see it and you feel that it is beautiful. Also, I think that what is mathematical ability? In a way, it is an ability to think for a very long time about one problem.
And sometimes you think about a problem and things that you never imagined that were true about a particular situation. All of a sudden, you see some pattern that you just...
For me, mathematics was, at that stage, and largely at this stage too, is an art.
Yes, yes.
Of course, it is very pleasant that it has so many applications. It's very nice. And in a way, this applied side is also beautiful.
In terms of your development, one of the things that we know when we recruit Russian students is they're exceptionally well trained.
Yeah, but the system is different, and it's a bit unfair to compare Russian undergraduates, in general European undergraduates, with American undergraduates, because in a way they start graduate school, well, at the age of 19 maybe. Here, they go to a college and they're still undecided about what they want to be. There they have to decide at 17. So at 17, I decided that I want to be a mathematician, and all my courses were courses in mathematics.
It's interesting from the point of view, I think, you know, how do mathematicians pick their problems? What is it that sort of motivates you? Obviously, one of the things that you did, which you're most famous for, is to solve something called the restricted Burnside problem. This is a problem in group theory, and for those people who don't know anything about groups, I have this one prop here for you, which is the famous Rubik's Cube, and you can think of this as a model of a group, because you can think, as you twist this, you get various positions, and you can think of the various twists as sort of generators, if you like, of how you get the positions. And one of the early problems this goes back to 1902 when Burnside formulated the problem, is he said, well, suppose I have a group with only finitely many generators. In this case, this has only finitely many generators because there's only finitely many twists that you can do. You can think of the positions that you can get out of this cube as being generated by these sort of quarter turns. And if you think of it that way, then there's various moves that will take you, if you do various quarter turns in a certain order, that will take you back to the same position you started with. This is called the order of a move, if you like. And the question of Burnside was, well, suppose that you have a group with only finitely many generators, and you know that if you do any move for n steps, you get back to the same position that you got. The problem of whether there's a biggest finite group for every d in n is called the restricted Burnside problem, and this is something that you solved in 1991. This is a problem that many mathematicians would just be afraid to attack, because obviously many people spent lifetimes just trying to understand this thing. And so what was it that motivated you to do this problem, and why did you decide to pick this particular problem?
Well, it's a very good question. Indeed. Well, you know, initially I heard about this problem from my first years at the university. It was popular in the Soviet Union. But I didn't start to attack it. First I started to build an infrastructure, you know, to work on related questions that possibly might be helpful. And then it was indeed a big decision that maybe I have a chance. Because, you know, there are these very clever people who worked on it.
Yes.
Why should I solve it? Maybe it's because I approached it from a different side. Maybe I knew something that they did not know 60 years ago. But initially it took some persuasion. I had to persuade myself that, yes, actually, I do have a chance. You know, like chess players, they look at the board and they even don't see how to win, but they can say which side has a winning position.
Yes.
So I thought, and I thought I might win.
How long did that process take you in terms of,
well,
once you decided that you got the sort of right approach?
The final storm maybe took about a year and a half, and that was very exhausting. The storm is when you think about it all the time,
right?
Basically 24 hours. You wake up in the night and still think about it. And then it better converge in a year or a year and a half, because, you know, it couldn't go on indefinitely.
That's often the case, that you know, mathematicians find that's the experience, that at some point you just get completely absorbed in the problem. Yes. And sometimes to the point of exhaustion.
Exactly.
Right, and you just can't do anything anymore. But in your case, that's actually that's very rapid, actually, to solve such a major problem.
But everything was prepared. And then when I finally understood that basically it is done, I didn't feel anything. I felt empty. That's it. Only empty.
People aren't very familiar with the Fields Medal and the ceremonies and all that sort of stuff. So maybe you can tell us a little bit about, how you first learned that you were going to be one of the people that were going to be awarded.
You know, the decision was taken in Paris, I guess. And at that time I was in Madison. But for people in Paris, maybe Madison, Michigan, they sound the same. So they sent a letter to Michigan. So I never heard about it. I was the last one to learn about it.
And what was the ceremony like for you in terms of, there were 3 other people who won it that year,
yes,
right?
I was very nervous, naturally.
And of course you had to give a talk at this course. I assume that was okay, right? I mean,
yes, there was a press conference when I had to explain what is a group. Well, I did not do it as well as you did.
One of the things that's happened just in recent years is we have something called the Clay Prizes. There's seven problems that people have come up with that they said if you could solve one of these problems, you get $1 million. So if anybody wants to get rich quick,
I don't think this is the quickest way to get rich.
So how is it that you actually came to the United States?
Well, first time I came to the United States in '89. Then that's when it became possible.
Right.
The Iron Curtain fell, and it was that fall. My first place was Yale University, and during that fall, I gave talks at 15 universities.
Wow.
In the United States.
So what was your initial impression of the United States in terms of, what you led to believe the United States was about?
The strongest impression was, how inclusive the place is. In a way, I came from Russia. There were people from, Belgium, England, China, and everybody felt at home.
Right.
Nobody felt a guest. And that was amazing, because I came from Russia, from the Soviet Union. In the Soviet Union, I happened to be of Jewish origin, and that was a very big issue there.
Right.
In America, it wasn't an issue at all. I could smell it. If you talk to officials in the Soviet Union, they would explain you that it also wasn't an issue. It was.
There's a beauty in mathematics that motivates us all, and I assume that that's the same for you, right?
Absolutely.
That somehow explaining these kinds of ideas to students and to your colleagues and communicating them is really the greatest joy. And one of the things that you're known for is being, a great lecturer, and I've heard you give lectures. And
sometimes you feel about some things that they're beautiful, and students very often tend to share your attitude.
In terms of your vision of your role within the university, I mean, how do you balance things like teaching and research?
I like to teach. I don't mind it at all, and I think that's nice for a mathematician to teach.
And you like teaching both undergraduates and graduates?
Yes.
And I know that you've had several, a series of graduate students since you...
When we teach calculus, in a way we teach the greatest mathematics ever invented.
Absolutely.
And I can come to the students and introduce them to the work of Newton.
Well, I want to thank you for spending this time with us, and thank you for coming to UCSD. I know that both the administration and the math department are so excited to have you, but it was a joy to talk to you today, and I'm glad you're here, and I'm glad you're in this office, and we hope that you're going to be here for a long time.
November 2002, UCSD broke ground on the world's first outdoor high-performance shake table. The new site builds on extensive testing capabilities already within UCSD's Charles Lee Powell Structural Research Laboratories.
The Powell Structural Research Laboratories are known for their capability to test very large, or in most cases even full-scale structural systems, to then validate the analytical models against the test results which we see in our laboratory experiments.
There are not too many places in the world where we could do
live tests, demonstrations of full-size models. This is one of the things that makes this lab so unique, the size of the equipment and the ability to handle, large infrastructure projects like the ones we have at Caltrans.
Located just 8 miles from the UCSD campus, the field station at Camp Elliott will be equipped with multiple testing facilities. For liquefaction and soil mechanics research, UCSD is building 2 interchangeable soil pits and 2 reaction walls. The Soil Foundation Structure Interaction Facility will be North America's largest facility for testing soil structure reactions to earthquakes and hurricanes.
The sheer size of the facilities allows us to test full-scale foundations and use actual construction equipment to install them. Secondly, the proximity of the soil pits to the shake table allow us to do systems testing. So we can put in a bridge foundation, a bridge abutment in the soil pits, and then use the shake table to actually excite the foundation and the bridge deck to look at the behavior of the entire system rather than just individual components.
The centerpiece of Camp Elliott will be the large high-performance shake table, the largest in the U.S. and the first outdoor shake table in the world, with powerful hydraulic actuators capable of shaking it at speeds up to 6 feet per second.
We can build full-scale structures then on this shake table, no height limitations, that's why we want to do it outdoors, no lifting capacity limitations, where we can then test full-scale structural systems under real earthquake input by shaking the base of the building to see the effect of earthquakes on actual structural systems.
The direct correlation between a model that is 1/10 the size of a building and one that is full size is speculative at best. Camp Elliott is going to provide a very important link in this chain.
Researchers from across the country will have access to the facility, even remotely, doing experiments via the internet. The Camp Elliott Shake Table is underwritten by the National Science Foundation's Network for Earthquake Engineering Simulation, Caltrans, and UCSD, and the university is now looking to the private sector for financial support to help with construction and startup costs, money that will ultimately benefit society as the Powell Labs pioneer new ways to keep structures safe in the face of earthquakes and terrorist attacks.